Okay, we're taking a look at the energy for life. We are in the book, The Living Earth. So remember, if you click that drop down arrow, you've got your three different texts. We're in the Living Earth, just as previous. We've already finished unit number 1. We're moving into unit number 2, Energy, Matter, and Life, and we're going to start with the Energy for Life 2.1. Prospectively, you can see that we're going to talk about photosynthesis, cellular respiration. We'll get into nutrient cycles, and then we'll get into mechanical and chemical weathering and erosion and deposition. So these first 3 units are going to be all about energy, or not these first 3 units, these first 3 concepts are going to be about energy. So click on 2.1. And let's just jump into Explore. Note that there are 6 Explore pages. The first one, what is energy and how does it contribute to maintaining life on Earth? That's going to be the focus there. It's how living organisms use energy. Okay, so go ahead and write down the date, set up your Cornell notes, and write down that essential question. And then why don't you answer it? Okay, pause your video and tell me what you think, or hopefully what you know. Okay, hopefully you wrote something down there. Roman numeral 1, we're going to take this living organisms and energy. That'll be Roman numeral 1 there. And if we take a look at the first paragraph there, generally, within your first sentence or two, you get the main idea of that paragraph. And it says all living organisms require energy to perform essential cellular processes. We went ahead and just took that at face value. That's letter A. All living things require energy. You require energy. Your dog and your cat require energy to carry on everything that defines us as living. And that gets right down to the cells in our body. So we use this energy for growth. Can't grow without it. Can't reproduce without it. And these are things that define life, right? We use this energy also to build molecules. If you want to go from a small molecule to a larger molecule, that is going to require energy. We use this energy to move molecules and atoms from low concentrations to high concentrations. You can see in this little diagram that I drew for you, on the left, you got maybe 3 molecules or atoms, and you want to push it. Literally, you want to push it against a concentration gradient. On the right-hand side, there's more molecules. These molecules on the left aren't going to just want to diffuse over to the right-hand side. Because there's already enough of them on the right-hand side. It's going to require work to push against that. So that little vertical line there represents a membrane. You can see on the left-hand side, I wrote low concentration because there's only a few atoms or molecules. On the right-hand side, we wrote the word high concentration just to help you understand that. And it requires energy to move against concentration gradients. Continuing in that first paragraph, other cellular functions, whether you're moving, whether your brain is sending an electrical signal through your spine to your legs to move, these require energy. Okay, so energy is certainly required. Where does that energy come from? Paragraph number 2. Ultimately, it says the energy comes from the sun. Yes, radiant energy, right? What you might think of as solar energy is fortunately there's a life form on Earth that is able to take that and convert it into food for itself. That process is called photosynthesis, and we usually think of plants as being able to do photosynthesis, right? There are some other organisms, bacteria, cyanobacteria, which also are able to perform this function. So, what do they do with that energy? How do they take the sun's energy and change? Because you can't create or destroy energy. So, how do they transform it? Well, they take that energy and store it in chemical bonds, usually sugar. And if you go all the way to the right hand side there, you can see whether you have an animal or us. We eat the plants, we are eating that energy. If we eat the animal that ate the plant, we also are getting that energy. Okay. All right, so kind of just continue to move on there. Um, Molecules containing energy are broken down when we eat them. Um, this is the process of cellular respiration. It's exactly the opposite of photosynthesis. In cellular respiration, you are taking the energies locked up in those chemical bonds and releasing that so that you can use it for other things. Those other things we already talked about at the beginning. Okay, so if we continue to scroll on down, we get into the next section here. Just kind of make sure you guys all have this notes there. Defining energy. How do you define it? Energy is the ability to do work or to cause change. Um, Cells convert energy from one form to another. That's true. We just talked about that. Um, they'll take a molecule of sugar and break it down and convert it into releasing the energy when they break it down. A little bit of review here. You recall that there is kinetic energy. There's various forms of kinetic energy, abbreviated with the letters KE. It is the energy of movement. Thermal energy is the heat generated by the kinetic energy of atoms or molecules. Your body generates this heat, right? You can feel the heat coming off of your body. That is the thermal energy of atoms and molecules. There is also potential energy, abbreviated with the letters PE. And if you recall, we say that potential energy is stored energy, and there are various forms of potential energy. In this case, we're talking about chemical potential energy stored in the chemical bonds. So if you continue to kind of scroll down there, what is energy? Energy, if we take a look at this paragraph here on the left, is defined as the ability to do work, and work is defined as the force used to move an object for a certain distance. So we went ahead and kind of wrote that down there. Energy is the ability to do work, defined as the force used to move an object a certain distance. And that's why we say that work equals force times distance, and that would equal a joule, or 1 Newton times a certain distance, meter. Okay, so joules is our standard measure of energy. It is not the form of energy that we usually talk about in life science or biology. We usually talk about calories, but anyway, that a joule here, 1 Newton of force is used to move an object 1 meter. Another term that they discuss is the watt, second paragraph here. A watt is defined as the use of 1 joule per second. We have that written down here. And letter E, we said that, and we're just kind of tracking right along with our text. Energy in food is often measured in calories, little c. A calorie, cal, is the amount of thermal energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. A side note here, calories on your food labels are usually referred to as kilocalories. kilo meaning 1,000, so 1,000 calories is a kilocalorie. And this is what they usually are referring to on your food labels. And typically, when they're referring to these food calories, they'll use a capital C to represent that, okay? And our final note there, in biology, the calorie is the most commonly used unit of energy. Maybe not for a physicist, right? But for a biologist, yes. Okay, well, that takes us right to the end of our notes there. Hopefully, as you're taking these notes, you're being thoughtful, you're reflecting and thinking about what is actually being communicated here. All right, well, go ahead and hit pause and write your summary paragraph, and we'll talk to you soon.